In this video, I'm going to derive the kinematic equations using the area under the curve. And that means I'll be doing it as a graphical representation. You can also do it totally analytically if you've had calculus. But if you haven't had calculus, this is a nice method to be able to understand where the kinematic equations come from. The kinematic equations are only useful in the special case where the acceleration is constant. This is my notation for constant acceleration. The acceleration at any time is equal to the initial value of the acceleration. This is what a graph of that would look like. We know that the average acceleration is equal to the change in velocity over time. We can rearrange that so that we get delta v is equal to the average acceleration times the time. I didn't write the subscript because I'm just going to immediately jump to, if the acceleration is constant, if you take the average of the exact same value, you just get back that one value. So the average acceleration is the same thing as that constant acceleration value. So as I've mentioned before, this is just the area under the curve, which is a rectangle as long as the acceleration is flat. Can represent the area under the curve as the length times the width, and so this is just the area under the curve. It's usually written with my notation where I let the t sub 0 means the time at 0, and in this case we're going to start from time equals 0, so delta t is just going to become t. And delta v, instead of v final minus v initial, we're just going to say v at any time t minus the initial velocity. So I'll plug both of those things into here, and this becomes v minus v0 equals a0 times t. One more step of algebra, and that's how we usually write it. I just add that v0 onto the other side, v0 plus at. This is the first kinematic equation, and I derived it using the area under the curve. Now we take this velocity, we can use the same idea of the area under the curve to find the position.